Hello friends, so we are presenting here a video on energy efficiency of a car heating system. My name is Kanika Vijayvargiya and my teammates are Jagdish Godara and Karthik Prajapati. So let us begin with a typical diagram of a car. So this is a car and here in its bonnet is shown a car heating system which has a heater casing, face vent, demister vent, footwell vent and inlet. We'll understand these parts in detail in the upcoming slides. Now let us first discuss about a typical car heating system. So this is a diagram of a heating system in a car which is well labeled. We'll see this in a little bit more detail in the upcoming when we'll discuss about the individual parts and their functioning. Now the key components of the heating system are a heater core, a blower motor or a fan, heater hoses, heater control valve, the HVAC, that is heating, ventilation, air conditioning control panel or assembly inside the cabin, coolant, thermostat, radiator and water pump, or we can call it a cooling system. Now this diagram details all these parts and we can see the functioning of each component. So the heater core is like a small radiator that acts as a heat exchanger. It is usually mounted under the dashboard or HVAC housing near the firewall on the passenger side of the vehicle. This component has an inlet and outlet to allow coolant to flow through the core. The blower motor blows air through the heater core and to the passenger compartment inside of the automobile. Next is the heater control valve. It is the device that controls the flow of the hot engine coolant through the heater core. It is usually located in one of the heater hoses to regulate this flow. This valve helps to control the heater output into the cabin as called for by the heater controls that are operated by the vehicle cabin's occupants. Now let us understand how this whole system works. So this is a diagram showing the functioning of a heating system. This is a simplified diagram, so let us first discuss it in brief. That is, first of all, the heat is absorbed from atmosphere, then heat is compressed and turned into heating. Heat heats cold air in cabin and raises temperature. Heated air is blown into cabin. Finally, decompressed heat turns into low temperature heat. Now let us discuss this in detail. So the heat that is created by the engine operation builds up and needs somewhere to go. Much of this heat is directed through the exhaust system. The remaining built up heat remains in the engine casting, transferring to the coolant. Once the vehicle gets to operating temperature, the thermostat opens and allows the coolant from the cooling system to circulate through the engine passages, removing the heat from the engine, sending it into the radiator and circulating to the heater core that distributes this heat into the cabin of the vehicle. Now the heater controls and blower fan are operated by the passengers in the vehicle to control how much heat comes into the cabin and at what rate by the speed of the blower motor or fan. Now let us discuss about the factors that affect the efficiency of the heating system. So the engine cooling system of the vehicle is directly linked to the heating system. Properly maintaining the cooling system is key for the heating system of our vehicle to work efficiently. Having the coolant in our engine flushed regularly and refilled with the clean coolant water makes is very important, along with repairing any leaks that occur in the cooling system. Now the coolant being at a full level with no leaks is also very important for proper operation. The thermostat needs to be opening and closing at the proper temperature levels and not sticking, and the water pump needs to be working so it can circulate the coolant through the engine, radiator and heater core. The heater core and radiator need to be kept clean out and leak free to be able to disperse the heat from the engine properly. Now I'll hand over to Karthik for the rest of the part. He'll explain the modeling part and the different balanced equations.
Hi guys, now I would explain about the cabin heat transfer subsystem. So, in the cabin system, the air in the car and the windscreen will be considered. Four quantities or states were identified to be relevant for the objectives: air temperature, absolute humidity, carbon dioxide concentration, as well as the windscreen surface temperature for the fog detection. So, this is a typical figure showing a car cabin and the entry and exit of different heats into and out from the system. This is a flow diagram showing cabin heat transfer subsystem. Now, we will see how to evaluate the car cabin temperature. In a car, we have first the desired and controlled airflow from the HVAC unit. The amount of air blown into the cabin will also leave it in a steady state. These two heat flows are denoted by Q in dot and Q out dot. The sources not connected to airflow are the heat transfer through the car body Q cap dot and the solar radiation Q r dot. These two influences can in most cases be regarded as static or slowly changing over one trip. Transient heat sources are the thermal masses in a car. For heating a car in the winter, a lot of energy is used to heat up the seats, the car body and other parts. This heat source or sink is named Q mass dot. Other influences on the temperature in the car are often hard to quantify and will be summed into Q other dot. This can be air leakage, the passengers in the car, electronics or heating from the engine. There are additional disturbances like open windows or doors which are important to the air temperature. They are covered by others since they are unpredictable and hard to compensate for. The figure shows all the heat flows and approximately where they occur in the car. If the sum of these influence is unbalanced, that is not equal to 0, a change in the thermal energy of the air in the cabin E air cap occurs, giving us a differential equation. So, this gives us the following differential equation. The literature formulas for most of the heat flows. They are extended and a parameter for the fraction of recirculated air mu recirculation is introduced. Here m air cap is the air mass in the cabin, Cv air is the specific heat capacity of the air at constant volume, m air in dot is air mass flow through the car, mu recirculation is the percentage of m air dot in being recirculated, Cp air is a specific heat capacity of the air at constant pressure, and A cap upon R cap is heat transfer through the car body. So, further Mi dot Ci is heat capacity of the parts of the car interior and body, T is the time, Q heat dot is thermal power of the HVAC system heater, T cap is mean temperature of the air in the cabin, T out is temperature of the air leaving the cabin, Aj is the window area, alpha j is the angle between surface normal of j and direction to the sun, gamma j is transmittance of j, Q sun dot is the sun intensity. Interior parts and the air are assumed to have the same temperature here. This is not correct. However, since the sun influence heats up the interior much more than the air, if this was considered, a more complicated model will be required, introducing the surface temperature of the interior as a new state. The outlet temperature T out will be simplified, set equal to T cap. Different approaches to estimate this temperature are suggested, but they are only valid without recirculating air and for standard car layouts. The heat transfer of the car A cap upon R cap can be calculated by summing up the contributions of all the cabin parts. So, this is the equation A cap upon R cap is equals to summation n equals to 1 to n surfaces and the terms. While the thermal conductivity K and the material thickness D and area A are usually known in constant, the convection heat transfer coefficients on the outside H AF out and inside the cabin H cap in depend on the airspeed. Literature gives us the approximations for those correlations. H cap in is proportional to the mass of the air to the power of 0.5 and H cap out is proportional to the velocity of air to the power 0.8. The temperature of the air blown into the cabin can be expressed with the following equation, and on combining all the equations derived so far, we can have the differential equation for an estimation of the mean temperature of the cabin. So, now we will discuss the energy efficiency. Because of the heat transport, a heat pump can produce more heat energy than it consumes through the compressor in the form of electricity. The efficiency is therefore indicated by the so called coefficient of performance COP. It is defined as the energy Q heat delivered in the heating case divided by the electric energy W compressor consumed by the compression. A physical upper limit is given by the ideal lossless COP of a Carnot process. So, this is the equation for the heating. COP heating is equals to Q heat upon W compressor, that is less than equals T sink plus 273.15 degree centigrade upon T sink minus T source. And for the cooling case, the extracted heat Q cool is compared to the compressor energy, and upper limit can be given by the ideal process, and here is the equation given COP cooling.
Now, in our further work, we will configure system inputs, that is predefined or manual. Then we will plot psychrometric chart for cabin air, and we will explore finally simulation results. And this can be explained as we will discuss about heat balance on the heating system. Then we will determine variables which can affect efficiency like humidity and mixing of air, and we will see how do we maximize energy efficiency. Then we will understand reduce, reuse and recycle, that is where and how these 3 R's can be applied to maximize efficiency. Finally, we will perform a theoretical study of installation of special equipment which can save heat energy, which will be followed by design of controlled algorithm for energy efficient heating system. So, this was about a car heating system. We hope you enjoyed it and liked it. Thank you and have a nice day.